Now let's see the relationship between matching and vertex cover. This relationship we need to study. What do you think? See, this is actually, these things are very simple. Let me tell you. All these things, all these relationships, these are actually very simple. In the last class, we have seen vertex cover and independent set, right? So for this vertex cover and independent set, we have seen this type of scenario. For example, if this is your independent set, then this will be your vertex cover. So this type of thing we have seen, right? Similarly, we have seen that if this is your vertex cover, then this will be your independent set. Okay. So this type of, this proof we have seen in the last class for vertex cover and independent set. This proof we have already seen. Okay. So similar proof you can do for this matching and vertex cover also. Like, okay, like just use the definitions, nothing else. So let's see. So this is the idea that cardinality of any matching, cardinality, remember, size of any matching. It does not need to be maximum matching. Okay, it does not need to be maximum matching. Cardinality of any matching. So size of any matching is less than or equal to, size of any vertex cover, is less than equal to size of any vertex cover. So this is interesting. And how to prove it? How to prove it? See, this is the hint to prove. Take any matching of size k. You take any matching of size k, and what you prove? You prove that any vertex cover. I am not talking about minimum vertex cover. See, please, I am not talking about minimum vertex cover. I am not talking about maximum matching. I am saying any matching you take. So any matching you take of size k, then what you prove? You prove that every vertex cover must have size greater than equal to k. So how to prove this? This is very interesting, and this is like very simple also. So for example, if you have a matching, just think about it. Let us assume you have a matching. Let us assume you have a matching of size 3. Let us assume you have a matching of size 3. Matching of size 3. Okay, you take a matching. So there exists a matching of size 3. Let's assume. Okay. So if you have a matching of size 3, what it means? Tell me what it means. You have matching of size 3. What it means? It means you have these three edges. You have A, B, C, D, E, F. This is your matching, correct? This is your matching, right? Yes or no? Okay, let's assume you have a matching of size 3. So this is your matching. Now tell me one thing. Any vertex cover, if I create any vertex cover, vertex cover should cover all the edges. Yes or no? It should cover all edges. It should cover all edges. Okay. EF. Okay. EF. So A, B, C, D, E, F. Now, vertex cover should cover all the edges. If I need to cover all the edges, tell me, what can you guarantee? I need to cover all the edges. So tell me, okay, to cover this edge, E1, I have to take at least one of them, yes or no? Who can cover E1? Tell me, who has the capacity to cover E1? Who has the capacity to cover E1? There can be other, remember, there can be other edges. Remember, there can be other edges, there can be other vertices, there can be other edges. So let us assume you have matching of size 3. This is your matching. In your graph, you can have other vertices. Remember, please remember, your graph can have other vertices, other edges. Your graph can have anything. Okay, your graph can have anything. Your graph can be anything. Your graph can have anything. So this is your matching. Now tell me. So if you want to cover, because remember, vertex cover should cover all the edges. So if you want to cover this E1, then at least one of them you need. At least one of them you need, A or B. At least one of them you need. Okay, so if you want to cover E1, at least one of them you need. Either A or B. To cover E2, remember, these 6 vertices are different or not? Can I say these 6 vertices are different? A, B, C, D, E, F. Are they different? Yes, they are different because it is a matching. So yes, they are different because it is a matching. So if I want to cover this as E2, then I have to take C or D, at least one of them. And if I want to cover E3, then at least one of them I have to take, E or F. At least one of them I have to take. Remember, this can be anything extra, there can be extra, but at least vertex cover size must be at least 3. Is this proof clear? So if you have matching of size 3, then definitely your vertex cover should have size at least 3. Whatever vertex cover you take, whatever vertex cover you take, it should at least have size 3 at least. Okay, it can be more, but at least size 3 must be there. Is this clear? So similarly, if you have a matching, let's assume if you have a matching with size, let's assume you have a matching with size 2k. Let's assume you have matching with size 2k. For example, this is your matching. Let's assume a1 b1 a2 b2 and so on, ak bk. So let's assume this is your matching. In your graph you can have more vertices, other vertices, you can have other edges, you can have, okay, for example, this type of edges you can have, for example, this type of new vertices you can have. So your graph can have anything, your graph can have anything, but this is the matching that I'm taking. In your graph you have this matching, this is your matching in your graph. Now tell me one thing. So this is your matching, this is a matching. I'm not saying that this is a maximum matching, this can be any matching. Okay, maximum or I don't care. Okay, maximum, perfect, not maximum, anything. This can be any matching, this can be single edge, I don't care. This is any matching. So you have a size, you have a matching of size 2k. Now tell me, what can you guarantee about vertex cover? What guarantee can you give about vertex cover? What guarantee you can give about any vertex cover? Remember, any vertex cover should cover all the edges. Remember, any vertex cover should cover all edges. You should cover all edges. So what guarantee you can give for vertex cover? This vertex cover should have at least, okay, so sorry, size k, matching of size k, sorry for that, matching of size k. Because remember, this is the matching of size k. Is this matching of size k or 2k? On your screen, this is matching of size k or 2k? This matching has size k or 2k? Matching means set of edges. So how many edges you have? Only k edges you have. Remember, matching means a set of edges. Matching means a set of edges. So how many edges you have? Total k edges you have. So this is matching of size k actually. This is the matching of size k. Now tell me, so what guarantee you can give? This vertex cover size must be at least k, because vertex cover should cover all the edges. All the edges must be covered. Who has the capacity to cover even? To cover E1, you have to take A1 or B1. If you want to cover E2, you have to take A2 or B2. You have to take A2 or B2, and so on. If you want to cover EK, then you have to take AK or BK. Either you have to take AK or you have to take BK, or both. Or both. Either you have to take AK or BK or both. See, at least one of them you have to take. Maybe both. At least one of them you have to take, maybe both. At least one of them you have to take, maybe both. So for example, let's take example. Consider this graph. Consider this graph. Okay, A, B, C. Consider this graph. So let me give you a matching. Let me give you a match. Can anyone suggest a matching? Suggest any matching. Suggest a matching. This matching you can suggest. This matching you can suggest. Right? This matching E1, E2, E3. So this matching E1 you can suggest. Okay. Now tell me, vertex cover. Remember, this is your matching. So what guarantee I can give? What guarantee I can give? What guarantee I can give? If I, okay, remember, vertex cover should cover all the edges. All the edges must be covered. So to cover E1, at least one of them I have to take. At least one of them I have to take. At least one of them I have to take. But is it enough? Did we cover all the edges? Did we cover all the edges? No. So take B also. Take B also. Now it is vertex cover. Are you getting my point? So at least one of them we have to take. I am not saying that exactly one of them. At least one of them. For example, here you can notice both of them we have to take. We have to take both of them. Is this clear? The point, the concept is clear. Another example you can take. For example, let me take this A, B, C, D, E. Consider this graph. Give me a matching. Give me a matching. So this matching you can give me. Actually, for this graph, the matching number is 1. So this matching you can give me. So what can you say about vertex cover? What can you say about vertex cover? Remember, this is your edge. To cover this edge, at least one of them we have to take. At least one of them we have to take. At least one of them we have to take. Okay. So let me take A. At least one of them we have to take. Let me take A. And this is enough. And that's it. This is enough. Now we have covered all the edges we have covered. Okay. So like this. Is this proof clear to everyone? What is happening here? So if you have any matching of size K, if you have any matching of size K, any matching of size K, then if you have any matching of size K, then what it means? Then what it means implies any matching of size K. If you have an if there exists a matching of size K, it means what? It means there exists a vertex. It means every vertex cover. See, if there exists a matching of size K, then for all vertex cover, every vertex cover must have size what? Then every vertex cover has size greater than equal to K. Okay. So this is the idea. If there exists a matching of size K, if there is any matching, there exists a matching of size K, then every vertex cover will have size greater than or equal to K. So this same point I can also say that the largest matching. Okay, this same point can I say like this? From this same point, can I say that the largest matching from here? Can I say that the matching number will be less than equal to vertex cover number? Can I say this? Can I say this? The maximum matching, because remember, any matching you take, then the vertex cover size must be greater than or equal to this. So I can say if you take maximum matching, then I can say that definitely this mu is less than equal to beta of G. This is point you can say. So this is the idea. Okay. The cardinality of any matching, whatever matching you take, the cardinality of any matching is less than or equal to the cardinality of any vertex cover. And this proof we have already seen. And the proof is very simple. Okay. So what is the proof? Just visualize in your mind. Forget about it. Okay. Don't read the slide. Okay. Just close your eyes and visualize. Close your eyes and visualize. You have a matching. There are edges. You have a matching. So vertex cover should cover all the edges. So who will cover these edges of the matching? You have a matching. Vertex cover should cover all the edges. So who will cover these edges of the matching? So to cover these edges of the matching, there are other edges also, but to cover these edges of the matching, you need at least one vertex from each edge. At least one vertex from each edge you need. At least one vertex from each edge of matching you need. So vertex cover size should be greater than or equal to matching size. Is this proof very clear? How many students have very clear idea of this proof? Okay, clear? So these type of things you have. These are very simple things. So the maximum matching and minimum vertex cover. The maximum matching and the minimum vertex cover. What is the relationship between them? We have already seen that this is the maximum matching. This is your maximum matching. This is the matching number. This is less than equal to minimum vertex cover. So what is this? This is the size of maximum matching. This is your size of maximum matching. So the size of maximum matching is basically less than equal to, and what is this? This is size of minimum vertex cover. This is size of minimum vertex cover. Okay, so the size of maximum matching will be less than equal to size of minimum vertex cover. There is one more interesting thing. This beta, actually this vertex cover number is less than equal to double of matching, double of maximum matching. This relation, how to prove this relation? This relation is saying that beta means this vertex cover number is less than equal to twice the maximum matching number. Okay, how to prove this? Is this is also very simple proof, very simple proof. Let's assume you have a maximum matching. Okay, so assume that this is the maximum matching. Just assume. Okay, for a moment, let us assume that this is your maximum matching. A, B, C, D, E, F. Let's assume that this is the maximum matching. Remember, this is the maximum matching. This is what I'm assuming. So let's assume. If this is the maximum matching, then tell me one thing. Okay, please tell me one thing. If this is the maximum matching, then is there any age? Is there any age which is like this? Like which is not incident on these vertices? Can I say every edge is incident on these vertices? And every edge is incident on one of these vertices? Can I say? Can I say every edge will be incident on one of these vertices? Tell me why. Okay, this type of edge, is it possible? Is it possible this type of edge in the graph? See, in the graph, you can have this edge. In the graph, you can have this edge. In the graph, you can have this edge, this edge, this edge, this edge. In the graph, you can have these edges. In the graph, you can have these edges. But tell me, is this edge possible? Is this edge possible? Why this is not possible? Why? What is the reason? Please tell me the reason. Abhipsa, Akash, what is the reason? Yes, because this is the maximum matching. Very good. Abhipsa, very good, very good. See, because I am assuming this is the maximum matching. If this is the maximum matching, this is the largest matching, it means this edge cannot be there. If this edge is there, then if this edge is there, like if there are different vertices, let's assume x comma y, then if such edge we have, then what I will do? If I have this edge, then what I will do? Then there is a contradiction. There is a contradiction because if I have this edge, then there is a contradiction because I can include here. There is a contradiction that this is maximum. There is a contradiction that this is maximum because I can use it here. I can use it here, yes or no? So if I have this edge, then I have a contradiction. I have a contradiction. So what I can say, if you have maximum matching, so this is the idea. Okay, so this is a note you can take, and this is very simple point that, okay, every edge, okay, so if S is maximum matching, if S is maximum matching, then okay, this is a true false statement. Someone can ask you, like, if S is maximum matching, F is maximum. If S is maximum matching, then I can say every edge of the graph, okay, every edge of the graph, what I can say, every edge of the graph is incident on at least one of the vertices. Okay, is incident on some vertex, is incident on some vertex covered by some vertex covered by S. Is this clear? Tell me. So if S is maximum matching, because remember, let's assume you have a graph. This is your graph G, V, comma, E. This is your graph. In this graph, let's assume S is maximum matching. This is your maximum matching. So if this is your maximum matching, then what I can say, because this S is maximum matching, this is your S, and this S is maximum matching. For example, A, B, C, D, E, F, G, H. Let's assume this is the maximum matching. If this is the maximum matching, then every edge of this graph, for this graph, every edge must incident on these vertices. Every edge must be incident on at least one of these vertices. Every edge must, for example, this type of edge also can be there, no problem. Okay, this type of edge can also be there. This type of edge can also be there. So this is possible. This is possible. This is also possible. Okay, this is also possible. This is also possible. But what is not possible? What is not possible? This type of, in G, this type of edge is not possible, like XY. This type of edge is not possible. Because if you have this type of edge, then there is a contradiction, and the contradiction is that if you have this type of edge, then array include this in S and get a bigger matching. So there is a contradiction that S is a maximum matching. If you have this type of edge, it means S is not maximum matching. Okay, So I can, this is the idea. Okay, so I can say this type of edge, x comma y, this type of edge not possible. This type of edge not possible. So very simple. So this is the statement. This is the theorem. This statement can come as true or false statement. Okay, tell me one more thing. See, the proof is not important in the GATE exam. The proof is really not important. Like no one will ask you the proof. But still, one thing you remember, the proof is not important. They will not ask you the proof, but they can ask you these small points which are from the proof. These small points they can ask you as a true false. For example, this question can come as a true false statement. There will be 4 options. One option will be like this. So, okay, so take care. Is this clear to everyone? So understand everything. Is this point clear? Is this statement clear? If S is maximum matching, then every edge of the graph is incident on some vertex covered by S. Every edge is basically every edge. Okay, so finally, if this is the situation, then what can I say? It means these vertices are covering all the edges. Can I say it means these vertices are covering all the edges? Okay. So from here I can say, that S, vertices of S, I can say vertices, okay, vertices covered by S. So I can say vertices covered by S will cover all edges, isn't it? Will cover all edges. Yes or no? Because already you know that every edge is falling on these vertices which are covered by S. Every edge is falling on these vertices which are covered by S. It means what? It means that vertices covered by S, these vertices which are covered by S, they will cover these vertices which are covered by S. These vertices will cover all the edges. So I can say these vertices covered by S, what can I name them? What can I call them? Vertices covered by S. What can I call them? Covered by S is, so vertices covered by S is what? So vertices covered by S is vertex cover. Yes or no? Is a vertex cover, because it is covering all the edges. So it is vertex cover. Okay, so this is the idea. Very simple. So this is the proof also. So finally I can say that these vertices is definitely a vertex cover. So I can guarantee that this is my vertex cover. I can guarantee that this will be my vertex cover. If I take all these vertices, okay, if I take all these vertices A, B, C, D, E, F, then I will definitely get a vertex cover. Okay, so this will definitely be a vertex cover. If this is a vertex cover, then what is the minimum vertex cover? Tell me. What is the size of this vertex cover? Please tell me. What is the size of this vertex cover? Size of this vertex cover. Size of this vertex cover. That is 2 of mu g. That is 2 mu. That is 2 mu. Yes or no? 2 mu. 2 into mu, because this is the number, this is the size of matching, means mu, size of maximum matching. So I can say this is the, now this is a vertex cover. Then what can you say about minimum vertex cover? Then if this is the vertex cover, this is a vertex cover, but I am not saying this is minimum. This is a vertex cover. I did not say that this is minimum. This is a vertex cover. So what can you say about minimum vertex cover? That is less than equal to 2 mu. Is this clear? If this is vertex cover, then the minimum vertex cover should be less than equal to this. Yes or no? If this is the vertex cover, then minimum vertex cover should be less than equal to this. And this is the idea. Did you understand this statement? This is also a GATE exam question. This is also a GATE exam question. Did you understand? Very simple. See, okay, so mu is less than equal to vertex cover is less than equal to 2 mu. So quite simple. For which graph? These, for example, if you take these graphs, like, okay, for which graph, this is my question. For which graph this will happen? For which graph mu will be equal to beta. For which graph this will happen? Mu will be equal to beta. Can anyone tell me? For which graph? Give me a graph. Give me a graph. Okay, for which graph? Like give one graph, I can say. Give one graph for which, give some graph. Okay, with, give some graph with this mu is equal to beta. Give some graph with mu equal to beta. So can anyone give me some graph where mu is equal to beta? Complete graph. No, 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 no. Complete graph is not correct. Complete graph is not correct. Cn with even vertices. Yes, this will work. Cn with even vertices. This will work. A, B, C, D. So here you can notice mu will be 2 and beta is also 2. Okay. So if you notice C even, if you notice C even, C even, C even, then you can notice that mu is also n by 2. Okay. Mu is also n by 2 and beta is also n by 2. So both are actually same. Complete graph is will not work. Remember, complete graph will not work because if you have complete graph, then for complete graph, what is the vertex cover? For complete graph, what is the vertex cover? The vertex cover is n minus 1. For the complete graph, the vertex cover is n minus 1. We have already seen in the last class. And what is the mu? What is the mu? Mu is n by 2. N by 2 floor. This will be the mu. Okay. So like this you can say. And complete bipartite graph. What can you say about complete bipartite graph? KMN. For this complete bipartite graph, mu we have already seen. Mu is minimum of m comma n. Okay. So tell me what is beta? What is the vertex cover? The vertex cover for this vertex cover, that will also be minimum of m comma n. That also will be minimum of m comma n, right? Vertex cover, because if you have this graph like km comma n, for example k2 comma 4 you have. Okay, let's assume you have k2 comma 4. Then vertex cover means which will cover all the edges. So this will cover all the edges. This will cover all the edges. Covers all edges. This will cover all edges. So I can say that okay, so I can say beta will be equal to 2. So this is the idea. So for KMN also, these will be same. But for complete graph, this will not happen. And for cycle graph C, even this will happen. And for C odd, for C odd, for C odd, this will not happen. You can just check. Okay. Now for which graph this will happen? Like beta is equal to 2 mu. For which graph this will happen? Beta is equal to 2 mu. Give a graph. Give graph with this feature. Beta equal to 2 mu. Yes, odd cycle. You can give odd cycle. You can give C3. You can give C5. So you can create C3, C5. You can create, or you can create complete. So okay, so C3, C5 you can create. You can also create K5, K7. You can also create them. You can also create complete graph on odd vertices. Basically you can create C odd, or you can create K odd. You can create C odd, you can create K odd. For example, if you have C odd, then what will be beta? For C odd, what will be beta? Beta means vertex cover. So what will be vertex cover? That will be n by 2 seal. The vertex cover will be n by 2 seal. And the mu will be what? Mu will be n by 2 floor. Mu will be n by 2 floor. So I want beta equal to 2 mu. This is what I want. Beta equal to 2 mu. Will it happen here? Will it happen here? Like for C3, it is fine. For C5, will it happen this? This will not happen for C5, right? So this will, okay, so for C3 this will happen, but for C5 this will not happen. Okay, so this is wrong. This is wrong. So for C5 this will not happen. Basically I can say K3, K4, K3, K5, these you can take. You can take K3, K5 and so on. Okay, so this C odd will not work. This C odd will not work. Okay, this will not work, but k odd will work. K odd will work. The beta k odd will be n minus 1, the beta will be n minus 1, and the mu will be n by 2 floor. Okay, the mu will be n by 2 floor. So this will happen. Okay, here it will happen. For C5, for C5, what is the, tell me, for C5, what is beta? For C5, beta is 3. And what is mu for C5? For C5, mu is 2. So clearly beta is not equal to 2 mu. You can notice beta is not equal to 2 mu. For every graph, beta will, this will always happen. This will always happen. For this, you don't have to apply your brain. I am asking when they will be equal. See, this will always happen. For every graph, this will happen. So here you don't have to apply the brain. I am asking when they will be same, when they will be equal. This is what I am asking. So they will happen when you have k equal to odd. For k equal to odd, this will happen. Okay. So very simple. So all these points we have seen. All the points. And this is just a for bipartite graph. This proof we will not see, and this is not required for GATE exam. This theorem is not required for the GATE exam, but sometimes what happens, this theorem is so popular. This is very popular. So because this is very popular, so sometimes in some poor test series, there you can find it, and then you will come to me and then you will say, sir, you did not teach this. See, this theorem is beyond the, I can say, beyond GATE level. This theorem is beyond GATE level, but this is very popular. Let me tell you, this is extremely popular theorem. So just this statement, we will not see the proof, but you can understand, but you can remember this statement. So this is for bipartite graphs. This theorem is for bipartite graphs. So this is only for bipartite graph. This theorem, what this is saying? This theorem, what this is saying? This theorem is saying what? This theorem is saying that if you have bipartite graph, then maximum size of matching is equal to minimum size of vertex cover. See, for any graph, what will happen? For every graph, what will happen? Like whatever graph you take, for every graph, what will happen? Whatever graph you take, for every graph, what will happen? Mu will be less than equal to beta. This will happen. Mu will be less than equal to beta, and this will be less than equal to 2 mu. So this will happen. But for bipartite graph, what will happen? For bipartite graph, what will happen? For bipartite graph, mu will be equal to beta. Okay, this is the simple point. This is what I'm saying. For bipartite graph, they will become same. They will become equal. Okay, so for bipartite graph, they will become equal. For every graph, this will happen. Whatever graph you see, this proof we have already seen. For this statement, the proof we have already seen. But for bipartite graph, this will happen, that mu will be equal to G. Mu will be equal to G. This will happen for bipartite graph. And this is known as Koenig theorem. This statement for bipartite graph, they will be same. This is known as Koenig theorem. Koenig's theorem. Okay. Is this clear? The statement, is this clear? The statement. This we have already seen. For every graph, this will happen. This we have already seen, that this matching number will be less than equal to beta. Beta will be less than equal to 2 mu. This we have already seen for every graph. For bipartite graph, what will happen? For bipartite graph, they will be same. But remember, this is just a this is a, I can say, this is only one way theorem. This is only one way theorem. So if you have bipartite graph, then this will happen. But if this is happening, it does not mean you have a bipartite graph. Is this clear? So if you have a bipartite graph, then what will happen? If you have a bipartite graph, then mu will be equal to beta. But remember, mu equal to beta does not mean bipartite graph. For complete graph, we have already seen that vertex cover will be n-1 and maximum matching will be n by 2 floor. This we have already seen. Okay, so all these concepts we have seen. Every concept we have seen. Okay, so did you understand? This is your all the concepts we have seen. edge cover, vertex cover, independent set, matching. All the four concepts we have seen. There are many questions, not many, but I think there are 5 or 6 questions in the GATE exam from these concepts. And the latest question is in 2022 from these concepts. There are 5 or 6 questions. Okay. But these concepts are very important in graph theory. And let me tell you one thing. See, whenever some concept is very important, then someday that question will definitely come in the GATE exam. They will make it easy. Okay. For example, some concept is very important. Let's assume, for example, I can say like matching. The concept of matching is very important. Okay. So someday they will definitely ask a question on matching in the GATE exam. They will ask an easy question, but they will definitely ask. Okay. Is this clear? So how many of you can say that you understood all of it, like all of them? See, proofs are very, very simple. All the proof that we have seen, these are very simple, yes or no? Every proof that we have seen, that is very simple. Did you understand the proofs? All the proof that we have seen, did you understand them? Okay. So let's see for this graph. Let's see for this graph, what is the matching? What is the matching number? Like A, B, C, D, E, F. What is the matching number for this graph? What is the mu of A? For this graph, mu. For this graph, what is mu? Matching number. Matching number will be what? So the largest matching you can create is like AB. You can take AB, you can take DC, you can take EF. So the matching number will be 3 and perfect matching exists. So here actually perfect matching exists. There is a perfect matching. Okay. So the mu will be equal to 3. And there is a perfect matching. You have a perfect matching. Okay. So this is the idea. And what is the edge cover? For this graph, what is the edge cover number? Like beta dash. What is the edge cover? Using edges, you want to cover all the vertices. Minimum number of edges you want to use, and you want to cover all the vertices. All the vertices you want to cover. If you want to cover all the vertices, then what I need to do? So you want to cover all the vertices you want to cover, then what you can do? You can do AB, you can do AB, you can do EF. Okay, you can do AB, EF, and you can do CD. So again, you can notice that this beta dash also will be 3. This beta dash is also 3. And for this graph, what will be the beta? Vertex cover. Vertex cover, which will cover all the edges. You want to cover all the edges. You want to cover all the edges. So vertex cover. So you can take B. This will cover these edges. See, if you take D, vertex cover, vertex cover, vertex cover. So if you take D, then it will cover all these edges. So now these edges are gone. These edges you have covered. Then you can take AE, AEF. Then you can take AEF. So the vertex cover number will be 4 actually. The beta will be 4. So if beta is 4, then what is alpha? 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 So you can notice that beta is 4. So then alpha independent set, alpha. So here you have 6. So that will be 2. Alpha will be 2. Can you notice what is the largest independent set you can create? What is the largest? Can you take D? If you want to create largest independent set, can you take D? To create, you want to create largest independent set, can you take D? If you take D, you cannot take anything else. If you take D, you cannot take anything else. So you cannot take D. If you want to create largest independent set, you cannot take D, because if you take D, you cannot take anything else. So finally, I can take A, E. So anyway, you can notice beta is 4, alpha is 2. Because we already know that alpha plus beta is equal to N. This we already know. Independent set vertex cover, that is equal to N. For this graph, all the data, this is your C6. For this C6, what are all the data? Tell me. First you tell me alpha. Independent set, that will be 3. Independent set. Vertex cover, what is the vertex cover? That also will be 3. What is the edge cover? You want to cover all the vertices. What is the edge cover? that also will be 3. And what is the matching? And what is the matching? That also will be 3. So for this C6, all things will be actually 3. All these things will be 3. Okay, let's see for this graph. So like this, for this graph, you tell me, first you tell me for this G2. Okay, find all of them. So what is alpha? What is beta? What is alpha dash? And what is beta dash? Tell me what is alpha dash? Alpha dash is same as mu. Remember, these are same symbols. So what is, okay, for this graph, you tell me what is alpha. For this graph, what is the independent set? The largest independent set that you can create. So you can take this vertex, this vertex, this vertex. These are you can take. So finally, the largest independent set, you, okay, so this is, if alpha is 3, then what is beta? If alpha is 3, then what is beta? So there are 6 vertices. So the beta also will be 3. Okay, next, what is mu? Matching number. Matching number. You can take this age, you can take this age, you can take this age. So the matching number will be 3. Okay, and what is beta dash? Beta dash means age cover number. What is age cover number? Age cover number, that also will be 3. How many edges you need? So for example, you need this edge, you need this edge. If you want to cover all the vertices, we want to cover all the vertices, so you need 3 edges. Okay, so these are the parameters. And what about for this? For this, what is alpha? For this graph, can you take this vertex? If you want to create largest independent set, you want to create largest independent set, can you take this vertex? You cannot take this vertex, because if you take this vertex, you cannot take anything else. If you take this vertex, so finally I can say you cannot take this vertex. So what is the largest independent set you can create? You can take this, you can take this, then you can take this. So finally I think you will create only 3. So I think alpha will be 3. And what is beta? What is beta? If alpha is 3, then what is beta? If alpha is 3, then what will be beta? That automatically will be 4. Okay, and what will be matching? What is the matching number? The matching number, remember one thing, matching number is always less than equal to n by 2. Okay, so you have 7. So basically matching number will always be less than equal to 7 by 2 floor. So matching number will be less than equal to 3. So what is the matching you can create? So matching number will be 3, because you can take this age. So basically you can take u1 u6, you can take u1 u6, you can take this, and you can take this. Okay, so matching number will be 3. And what is beta dash? Beta dash, age cover. Okay, edges which will cover all the vertices. We want to cover all the vertices, so that will be 4. Okay. And for this graph, just quickly tell me, for this graph, what will be alpha, what will be beta, what will be alpha dash? Alpha dash means mu, and what will be beta dash? All these things you quickly tell me for this graph. First, what is alpha? Alpha means independent set. What is the largest independent set you can create? This is the independence number, stability number. Stability number means size of largest independent set. So what is the largest independent set you can create? From this, how many you will take? Tell me, from these 3, how many you can take? From these 3, you can take only 1. From these 3, you can take only 1. So what I can do? I can take this, I can take this, I can take this. This is what I can do. V1, V3, V5. Okay. So this alpha will be 3. Alpha will be 3. I will take V1, V2. So basically this, okay, so this will be like V1 I can take, V3 I can take, V5 I can take. Okay, if alpha is already 3, then what is beta? Beta is already n minus alpha. So that will be, total you have 1, 2, okay, total 5. So 5 minus 3, that will be 2. So 2. Tell me which 2 vertices are enough to cover all the edges? Which 2 vertices are enough to cover all the edges? Which 2 vertices? Which 2 vertices are enough? So you can take V2, V4. These 2 vertices will cover all the edges. These 2 vertices, they are covering all the edges. Okay. Next, what is matching? What is the largest matching you can create? So you can take, for example, you can take this edge, you can take this edge. So the largest matching you can create is 2. And what is the edge cover? What is the edge cover? You want to cover all the vertices. So you have to take this, you have to take this. Okay, then you have to take one of them. So finally it will be 3. So far what we have seen, okay, so far this is the conclusion, or I can say summary. This is the conclusion or summary. Let me tell you the summary so far. First, we have seen that this is the summary so far. So you have a graph where you have G, V, comma, E. This is your graph. Then this is the summary, that first point. What is the first point? That alpha plus beta. Okay, so let me just write here. First of all, let me write what are these things. Like, first of all, let me write what is alpha. So tell me what is alpha? Alpha is independence number. Independence number. This is the size of largest independent set. Okay, so this alpha is basically the size of largest independent set. Size of, okay, largest independent set. So that you already know. Okay, size of largest independent set. Many times I have told you. So this is your independence number. What is beta? This is your vertex cover number. This is the vertex cover number. Means size of minimum vertex cover. This is the size of minimum vertex cover. Then what is mu? What is mu? This is the matching. This is the matching number. Size of largest matching. Size of largest matching. And what is beta dash? This is edge cover number. This is edge cover number. Size of, okay, minimum edge cover. So here what we want? Here what we want? Tell me. Here we want max or min? Here we want max or min? Max. Here we want min. Here we want max. Here we want min. Okay. Can you prove this? And this is very easy to prove. So just try this. And this is actually very easy to prove. Once I prove it, you will see that this is very easy to prove. So try this. Please try. Take a copy pen and think about it. Alpha means independent set. So the size of this independence number, the largest independent set, that is less than equal to edge cover. Okay, so try this. For any graph G with the delta, why this condition? Can anyone tell me? What do you think? Why this condition? This condition, why this condition? Delta means minimum degree greater than 0. To define, because remember this is independence number and this is your edge cover. Okay, so this is your independence number. This is the I can say this is the independence number. This is the largest independent set. This is your largest independent set size. And this is the minimum. This is the minimum edge cover size. So this condition we have so that we can define, okay, so that we can define to define edge cover, so that we can define edge cover. Okay, so this condition we have so that we can define edge cover. Else edge covering will not be defined. In this case, only in this case edge cover is defined. So this is okay to define edge cover. Now tell me, can you prove it that largest independent set means independence number is less than equal to minimum edge cover size? Means, okay, so this is less than equal to edge cover. See, the idea is very simple. Just observe these two things. See, idea is very simple. Observe these two things. Observe these two things. So if you have independent set, just think about it. Okay, if I give you this largest independent set, you have a graph G, V, comma, E, and in this graph, let's assume you have a largest independent set. So let's assume this is your largest. Remember, this is the largest independent set, and this largest independent set is like this. Okay, this is your largest independent set. Here, let us assume that this is the largest independent set, A, B, C, D. Now, what it means? If this is the let's assume, just assume that this is the largest independent set. If this is the largest independent set and edge cover, what edge cover will do? Tell me what edge cover will do. It should cover all the vertices. it should cover all vertices. Yes or no? Agree? Edge cover should cover all the vertices. It should cover all the vertices. So this edge cover should cover, it should cover all the vertices. So tell me one thing, for these four vertices, how many edges you need at least? You want to cover all the vertices. All vertices you need to cover. For these vertices, at least how many edges you need? For these vertices, if you want to cover these vertices, at least how many edges you need? Array, four, because this is independent set. So there is no edge which can cover two of them. We don't have any edge. There is no edge which can cover two of them. This is independent set. This is independent set means there is no edge which can cover two of them. There is no edge which is incident on two of them because they are non-adjacent. They are non-adjacent. There is no edge here. You don't have any edge here. So there is no edge which can cover more than one of them. More than one of them. So tell me, edge cover want to cover all the vertices. You want to cover all the vertices. So if you want to cover all the vertices, then tell me how many, for to cover these vertices, how many edges you need? So at least four edges you need, yes or no? E1, E2, E3, E4. At least four edges you need, yes or no? At least four edges you need. This you need for A, this you need for B, this you need for C, and this you need for D. Is this clear? Isn't it simple? This statement, this proof, isn't it simple? So if you have a largest independent set, for example, this is, let's assume this is your largest independent set. If this is the largest independent set, what it means? It means there is no edge here. It means there is no edge. It means there is no edge here. You don't have any edge between them. Okay. So because there is no edge, so there is no edge which can cover more than one of them. So if you want to cover these vertices, then you definitely need at least four edges. If you want to cover this vertex, then you need a different edge. This vertex, different edge. This vertex, different edge. So for these four vertices, at least four edges you need. So finally, what I can say? So this is the proof. Okay. So this is the proof. Is this proof clear? Very simple proof. Very simple. That alpha is less than equal to beta dex. So what was the summary? So you can notice independence number and all these things we have seen. So this is the summary. The first summary is alpha plus beta. This is equal to what? This is equal to number of vertices. Alpha plus beta is equal to number of vertices. Okay. Next, the second summary is the second relation that we have seen. What is the relation that we have seen? The second, I think this, that beta is greater than equal to matching number, and that is less than equal to twice the matching number. Okay. The third thing that we have seen is beta dash is greater than or equal to n by 2 seal. Beta dash is greater than or equal to n by 2 seal. This we have seen for all graphs. These things will happen for all the graphs. And what is the fourth? Okay, so if your graph is G, V, E, then what is the fourth thing? This matching number, this is less than equal to n by 2 floor. Next thing, what is the next thing? Okay, so these things we have seen, 3, 4. Is there any other? I think these are right. Okay, and we have also seen this. Alpha is less than equal to what? Beta dash. This we have seen just now. Alpha is less than equal to beta dash. Okay. And also what we have seen? We have seen Koenig's theorem. We have seen Koenig's theorem, we have seen. So if your graph is bipartite, then what it means? It means mu is equal to beta. Let me tell you just one more thing. You already know that alpha plus beta is equal to n, right? Yes or no? You already know that alpha plus beta is equal to number of vertices, right? This we have already seen. The proof we have seen. This is the most like cutest proof. Very cute proof. Very cute proof you have. Like if this is your independent set, then this is your vertex cover. So this is your very cute, like this proof we have already seen in the last class. Okay, yes or no? Actually, similar thing you can say for alpha dash plus beta dash. That is also equal to n. But the proof we will not see. The proof is hard. The proof is complicated. But okay, but you can notice both are actually similar. So these two statements are true. So alpha dash plus beta dash is also. What is alpha dash? What is alpha dash? What is alpha dash? This is your matching number. What is alpha dash? This is your matching number. Matching number means mu. This is your mu. Okay. And this beta dash is your edge cover. So this is the idea. Okay. So this is the complete explanation. Oh, this is the summary. We have also seen the summary. Is this summary clear? These things will help you. These things will help you. This will help you. This will help you. These things will help you a lot. Like this edge cover is greater than equal to n by 2 seal, and this matching number is less than equal to n by 2 floor. These things will help you a lot. This conics theorem will also help you. This conics theorem will also help you. This side is not true. Next, actually using this conics theorem, can you say for our, let me ask you, for hypercube graph. Let's see for hypercube graph. Hypercube graph Qn. For this hypercube graph, you tell me what is vertex cover? What is vertex cover? What is matching number? What is that? For hypercube graph, what is vertex cover? What is matching number? What is alpha? And what is beta dash? And what is beta dash? Remember? Remember. This hypercube graph is what? This hypercube graph is what? This we have already seen. This is what? This is a bipartite graph. This is a bipartite graph. This we have already seen. This is a bipartite graph. This hypercube graph. This is a bipartite graph. You already know the even parity, odd parity. The even parity, odd parity. This we have already seen. Okay. So this is your bipartite graph. And because this is bipartite graph, so what should happen? Because this is bipartite graph, so mu is equal to beta. So mu will be equal to beta. This matching number will be equal to beta. And what is the matching number? Remember, half vertices are here and half vertices are here. Okay, so what is the matching number? The matching number, what will be the matching number? The matching number will be half vertices are here, half vertices are here. For example, 2 power n minus 1 vertices are here, 2 power n minus 1 vertices are here. So the matching, so the matching number will be like this. You can create this type of matching, you can create. Okay, so like this you can create the matching. What is the vertex cover? What can I say about vertex cover? Because so this will be the vertex cover, yes or no? This will be the vertex cover. So finally here I can say 2 power n minus 1, because both will be same. Or you can create this type of matching, you can create this type of matching, you can create. And for Qn, what else you can say? For Qn, what is the independent set? What is the independent set? That is also 2 power n minus 1. This will be your independent set. This will be the independent set. This will be the independent set, because there is no edge here. You don't have any edge here. And if you have alpha, then beta will be number of vertices minus alpha. So that will be 2 power n minus 2 power n minus 1. That is also 2 power n minus 1. Okay. So like this you can do. So all these things we have already seen. Very simple. If anyone has any doubt, this is what we have to by heart. I told you. Okay. Proof complicated. Okay. So this is like, we already know. So this is actually, we know that alpha plus beta is equal to, this we already know, alpha plus beta is equal to number of vertices is equal to n. Similarly, okay, similarly, This is similarly. The proof you can skip. But these are actually simple because you already know this. So automatically you can understand this also. Okay, so this is our topic and this is the complete analysis and we have already seen. For this question, just quickly answer it. Remember in this question, matching means perfect matching. Basically this matching word, this matching word, this matching word, that basically means perfect matching. So replace this matching with perfect matching. So actually this should be perfect matching. This should be perfect matching. Similarly here, this should be perfect matching. Okay, this should be perfect matching. Anyway, so tell me, for which n complete graph will have perfect matching? For which n complete graph will have perfect matching? For which value of n? So you can notice that this kn has perfect matching. This has perfect matching. So when this will have perfect matching? If and only if n is even. Very simple. If and only if n is even. If your n is even, then it will have a perfect matching. If and only if n is even. Prove that if graph has matching, then number of vertices will be even. If graph has a perfect matching, this we have already seen. See, this matching basically this should be perfect matching. Here you must have perfect matching. Okay, so this we have already seen that if you have perfect matching, if your perfect matching exists, if perfect matching exists, then number of vertices will be even. We have already seen, but number of vertices even does not imply perfect matching. This we already know. Next, is the converse true? No, the converse is not true. For option C, the converse is not true. You can take, for example, A, B, C, D. This example you can take. Here you can notice number of vertices is even, but perfect matching does not exist. Okay. So this question was just you can try. Okay. Anyway, so this is enough. So we have seen all these concepts. Tomorrow we will start. Tomorrow our topic will be. Tomorrow we will start another topic, that is chromatic number, coloring. Coloring we will study tomorrow. Okay.